Okay. Good morning to all of you. So today we are going to discuss about the atomic structure. In this atomic structure class, basically I will discuss about little bit about the Bohr's theory and what is the drawback of that, and the wave nature of the electron, and based on the wave nature how we can have the Schrodinger wave equation, and how we can interpret the shape and the size of the atomic orbital by understanding the wave equation. So before going to start about the Bohr atomic model, you need to understand that Bohr's theory didn't came in a single day. So behind that there are a lot of efforts from various scientists, starting from Dalton to Rutherford, so that Bohr's atomic structure came into the picture. So when Bohr atomic structure came into the scientific community, before that most of the physical phenomena can be understood by the classical mechanics, which is governed by the Newton's second law of motion, or we can say the Newtonian mechanics. Subsequently, when the Newtonian mechanics developed further by Lagrange and Maxwell, scientists that time believed that there is no need to have a new theory, rather than to have a specific experiment so that the experimental error can be reduced. But the early 19th century or the end of the 18th century, there are different experiments came. The experiment results of those experiments cannot be explained by the classical mechanics. The first, this famous black body radiation, the black body radiation. Second, photoelectric effect, and third, the line spectrum of hydrogen. So by applying classical mechanics, these experimental results cannot be explained by the help of classical mechanics. So to understand those experimental findings, or to verify the experimental findings, Max Planck took a drastic assumption which states that the energy is not a continuous term but is a discrete quantity, and energy is proportional to the frequency. Earlier in classical mechanics or in the Maxwell electromagnetic theory, it tells that energy proportional to the intensity. But since Planck told the energy is proportional to frequency, if you can equate, then you will find E is equal to h nu. We all know this h is the Planck constant. So he further told that this particular h nu amount of energy he described is the quanta, and it's a discrete quantity. And once he applied this assumption, he can explain the black body radiation efficiently. After that, Einstein took the same assumption and could explain the photoelectric effect, and also it can explain the line spectrum of hydrogen. So that time Niels Bohr took this particular assumption and gave his famous planetary model. So according to that, we all know that there is a nucleus inside the atom, and the electrons are moving around the nucleus in a particular orbit. And he further told that if any electron wants to promote to the higher orbit, it will absorb some energy, and if any electron wants to come to the lower orbit, it will emit the energy. What amount of energy? The energy amount should be h nu amount of energy. So Bohr's atomic structure model based on the Planck assumption, and he assumed that the particle nature of the electrons. But the main drawback of the Bohr's model is that it cannot explain the atomic structure of the many electron particle or systems. The model only worked for the hydrogen-like atoms. The existence of fine or hyperfine structure in the spectrum line cannot be explained by this Bohr model. The Zeeman effect and Stark effect also cannot be explained by the Bohr model. So to explain those phenomena, we need to modify our atomic structure model, and the atomic structure model now governed by the wave nature of the electron, and the wave nature of the electron first introduced by scientist Schrödinger. And we have to remember that before Schrödinger gave his famous wave equation, the same time Heisenberg also introduced the quantum mechanics, but his quantum mechanics is based on the matrix algebra, which is relatively hard to understand. Rather, the Schrödinger wave equation, which is based on the differential equation. So to understand the Schrödinger wave equation, here Schrödinger took two assumptions. First, he derived the equation with the help of the wave nature of the electron, and also he took the wavelength as a de Broglie's wavelength. All we know, the de Broglie's wavelength lambda is equal to h by mv. So if I can take a normal wave equation or a oscillating wave which is oscillating along the x direction, the simple example, this, if I say this is my wave function, wave function generally denoted as psi. So psi is equal to a sine 2 pi x by lambda. So that means the wave is oscillating along the x direction, the wavelength is lambda, and a is amplitude. So if I going to do the first derivative of this wave function with respect to x, we can have d psi by dx, which will be equal to a cos 2 pi x by lambda into 2 pi by lambda. So if I do the further derivation d2 psi by dx2, then we can have minus 4 pi square by lambda square into a sine 2 pi x by lambda. So that means instead of a sine 2 pi x by lambda, I can easily put the wave function psi. So I can write the equation d2 psi by dx2 is equal to minus 4 pi square by lambda square into psi. Or if I just remove this equation and rewrite the equation as d2 psi by dx2 plus 4 pi square by lambda square psi is equal to 0. So this is a differential equation, and if you can solve this, we can have the information of psi. But rather, we from this equation we want to derive this famous formula h psi is equal to E psi. So now if I can put this lambda as a de Broglie's wavelength, I can easily put lambda is equal to h by mv. That means lambda square will be h square by m square v square. So if I put h square by m square v square in this equation, it will be like d2 psi by dx2 plus like 4 pi square m square v square by h square psi is equal to 0. Okay. So now we will do some modification in this equation so that we can at least have this type of expression. So this 4 pi square m 4 pi square m square v square I am writing as, I just multiply the numerator and denominator by 2 and I can have plus 8 pi square m square v square divided by 2h square. So now look at this half, this m square I can write m into m and v square. So half mv square is my kinetic part. So instead of half mv square, now I can write d2 psi by dx2 plus 8 pi square m into my kinetic part, energy part, divided by h square psi, which will be equal to 0. Okay. So we all know the total energy is a combination of E, I can write kinetic energy plus potential energy, or I can write potential energy in the form of V. So my kinetic energy is E minus V. So instead of this kinetic energy, now I can write d2 psi by dx2 plus 8 pi square m. Instead of kinetic energy, I am writing now E minus V divided by h square into psi will be equal to 0. Okay. So now I will do further modification by multiplying the whole expression by minus h square divided by 8 pi square m. So as a result, it will have minus a square by 8 pi square m d2 psi by dx2. Then it will be minus E minus V psi is equal to 0, or I can write plus V psi is equal to E psi. Now look, if I compare this expression with this H psi is equal to E psi, I can have this E psi here, and if I take the common psi, now this particular term will be there, 8 minus h square by 8 pi square m. This grad square instead of grad square I can write here is x square plus v psi. So this part is nothing but this h. What is h? This is an operator, and in quantum mechanics we say that this is a Hamiltonian operator. So this Hamiltonian operator, now it's a combination of the kinetic energy part and the potential energy part. So in that sense, I can say the Hamiltonian operator is also an energy operator, because if I apply this operator on this wave function, I can have energy of this particular wave function. Okay, so here one thing you need to remember, that this operator is nothing but a mathematical symbol which operates on a particular function and gives you certain values. So in such case, when after operation, if you get a constant value with the same wave function back, that type of equation we can say it's an eigenvalue equation or eigenvalue expression, where the constant value E is called the eigenvalue and wave function will be determined as eigenfunction. So here I have written this Hamiltonian operator operates on an eigenfunction, gives us the eigenvalue and the same eigenfunction back. So that means for a particular wave function you can have a particular energy. That means energy is not going to a continuous term, it's a discrete quantity. And by solving the Schrodinger equation you can have different allowed energy values. Okay. So here you need to understand one thing. In exam we used to give, let's say, examine whether psi is equal to e to the power ax is an eigenfunction or not. If I give you the operator ddx, so for that you have to do ddx of this wave function and it will give you e to the power ax. No. So it will give you x. So it will give you a into e to the power ax. So e to the power ax also I can write a into psi. That means ddx my operator, psi is a wave function, a is my constant value, and I can have the same wave function back. So I can say this is a eigenfunction and a is my eigenvalue. But if I say the wave function psi is equal to e to the power ax square, then instead of a I can have 2ax into e to the power ax square. In that case also I can have the same wave function, but since this is not constant and it depends on the value of x, so I cannot say psi is equal to e to the power ax square is an eigenfunction. So most of the cases we are dealing with the Schrodinger wave equation, which is eigenfunction. But what beauty of this Schrodinger wave equation is, every solution of this Schrodinger will not be satisfy the following condition. If it is satisfied these three following conditions, we can say that this is an allowed or acceptable solution, which are the psi must be a single valued, psi must be continuous, and psi must be finite. Okay. So for an atom we can have several wave function. That means we can have several energy states depending on the wave function. And these wave functions are called as orbitals, which is analogy to the orbits of the Bohr theory. Okay. So each orbital can be described by the quantum numbers. We all know there are 4 quantum numbers: principal, azimuthal, magnetic, and spin quantum number. But to know the orbital characteristics about its size and about its shape, we need to know only these 3 quantum numbers, which are principal quantum numbers, azimuthal quantum numbers, and magnetic quantum numbers. So here is a small description of each quantum numbers. Principal quantum numbers n is given by this expression, and this principal quantum number gives you the size of the orbitals. Similarly, azimuthal quantum numbers gives you the shape of the orbitals, whereas the magnetic quantum number gives you the orientation of the orbitals in the 3-dimensional space. So till now what we discussed, this particular Schrodinger wave equation, what I have showed you in the derivation, this is based on the Cartesian coordinate, but this Cartesian coordinate form cannot be used for the atom, since we know atoms are spherical in nature. So we need to convert this xyz into spherical coordinates r, theta, phi, and help of the trigonometry you can easily do that, easily transfer that xyz into r, theta, phi. And one advantage of doing xyz to r, theta, phi is that instead of 3 variables xyz, in r, theta, phi you can have only 2 variables. These r variables, which is called distance variable, and theta and phi, they are the angle variables. Okay. So now you can actually separate the full wave function, which is described in the spherical coordinates r, theta, phi, into 2 parts. one is the distance part and another is the angle part. Okay, so distance variable, we say this is the radial component. This gives you the size of the orbital, because if you increase the r, you will increase the size of the atom orbitals. And if you vary this theta and phi, you can actually have the shape, different shape of the atomic orbital. So this r theta phi now divided in two parts, one the radial part and one is the angular part. The radial part depends on the principal quantum number and the azimuthal quantum number, whereas the y part or angular part depends on the azimuthal quantum number and the magnetic quantum number. Now this angular part determines the shape and the orientation of the orbitals, or this magnetic quantum number also gives you the information about the different subshell present in the p or the d orbitals. Okay, so here everything is okay. So now to understand the nodal surface of atomic orbital, nodal surface means the probability of finding electron in that area is 0. So that means my wave function will be 0 at that part. So radial nodal surface means this r part will be 0. If it is angular nodal surface, that means this y part will be 0. R part 0, that determines the radial nodes. Y part 0, that determines the angular nodes. And this r part, how to find how many numbers of radial nodes or angular nodes present in atomic orbital? The simple rule says that for radial nodes the number is n minus l minus 1, where n is the principal quantum number, l is the azimuthal quantum number. So if I say, I can have the example, if I say 1s, that means my n is equal to 1 and for s, l is equal to 0. So for 1s there will be n minus l minus 1. So 1 minus 0 minus 1. So there is 0 number of radial nodes. Simply for 2s, then n is equal to 2, l is equal to 0. That means you can have 1 radial node. So that means if I have the 1s geometry here I have said this 1s, then 2s, because of the larger number of r, so the size of the orbitals is increased. Why increased? Because the presence of this radial node. So just because of the radial node, you can have the increased size of the atomic orbital. Similarly, for 3s, there will be 2 radial nodes, so further the size is increased. But remember that for 1s or 2p or 3d, there will be always 0 number of radial nodes. Similarly, for the angular nodes, where the wave function becomes 0, that means my y, l, m, l, theta, phi is equal to 0, and the number of angular nodes can be determined if you know the azimuthal quantum number L. That means for 1s, just because of L is equal to 0, you have 0 number of angular nodes. But for 2p, because L is equal to 1 for p orbitals, you can have 1 angular node. Okay. And for 1s, 2s, 3s, for all s orbitals, there will be 0 number of angular nodes. For all p orbitals, there will be only 1 number of angular nodes. For all d orbitals, there will be 2 number of radial nodes, which indirectly supports that just because of the presence of one angular node, the p orbital is your dumbbell shaped in nature. Okay, so if you can know the principal quantum numbers and azimuthal quantum numbers as well as the magnetic quantum numbers, you can easily determine how many numbers of radial nodes or angular nodes present. In a sense, what will be the size and the shape of the atomic orbitals. Okay. So now, if I give you some wave function, how to determine which part belongs to your angular part or which parts belongs to your radial part. So this is a typical example of 1s wave function. Here this z is nothing but the effective nuclear charge, a0 is the Bohr radius, and this density rho is nothing but follow this expression, r is the distance from the nucleus, and n is the principal quantum number. So simply, if you look at the wave function, how far your r dependency is there, up to that part there will be radial part, and rest of the part will be the angular part. So if this expression, up to this you have the r dependency because this rho depends on r. But here there is no theta or phi dependency. So I can easily say this is my radial part and this is my angular part. Look at this is the psi 1s. That means your 1s orbital or any s orbital, the angular part is not dependent on the theta or phi. That means it is independent of the angles. So that is the reason the s orbital always spherical in nature, just because of the not dependence on theta and phi. So if I give you the equation and ask to find the radial part and the angular part, simply you can write this is the radial and this is the angular part. Okay. Now go for the p orbital. Here is the typical pz wave function. Here also you can see up to this there will be r dependency, and here this part will be angular part. But the question you can ask, this small jet and this jet by r, so this will be r dependency. But this capital Z and small z, they are different. Capital Z belongs to the effective nuclear charge, but this small z belongs to the Cartesian coordinate xyz. If I simply write this z is equal to r cos theta, then this r will be cancelled. So the angular part only depends on the cos theta. So for pz orbital, the size depends on the cos theta term, and also because of this z direction, you can say this is the pz orbital. So simply if you vary the theta, you can have the shape of the p orbital. Simply I can take, this is my z direction and this is the variation of angle theta. If I put cos 0, that means it's a value of 1. Suppose here is 1, and cos 90 becomes 0, cos 180 becomes minus 1, and cos 360 again 0. So in between 0 and 90, if you vary the angles, so you have a non-zero term, and if you add that, you can have this type of shape. Once it crosses the 90, again all the cos term will be negative and attains the minus 1 at 180, and subsequently if you complete the cycle up to 360, you can have the dumbbell shaped orbital which is oriented along the z direction. So simply for 2pz, it depends on the cos theta because z by r. If you change pz to px, it will be x by r, and if you change to y, it will be y by r. Or simply if you put x is equal to r sin theta cos phi or y is equal to r sin theta sin phi, you can have the px and py orbital shape depending on the variable of theta and phi. So these are the representative pictures of px, py and pz orbitals. So simply you can have the, because of this single variable x, y or z, you can have a one dumbbell set. But for the d orbital, if you see the d orbital wave function, I omit this radial part. This is the angular part. Here you can see it depends on two variables x and y. So that means you will have two dumbbell set orbitals for d, or also for the number of angular nodes, also you can see that d orbitals has two number of angular nodes just because of these two different dumbbell set orbitals. Okay, so these are the subsequent wave function for x square minus y square and z square z square orbitals. One question we can generally ask from these or d orbitals, that for x, y, y, z and zx, the orbital lobes are situated in between the axis, whereas the x square minus y square or z square, these orbital lobes are situated along the axis. What should be the probable region for that? Suppose for x, y orbitals, that means my angular part is depend on x, y by r square. So to understand the nodal surface, we know the angular part should be 0. So that means the xy by r square, this part should be 0. When this part should be 0? Either x is equal to 0 or y is equal to 0. If it is x is equal to 0, that means it's a yz plane. So along the yz plane, there will be electrons, and x is its axis, there will be the probability of finding electron is 0. Similarly, if y is equal to 0, then it will be xz plane. So along the x and y axis, there will be no electron. So in between the orbitals, there will be more electron density. So that's why x, y, y, z and zx, their orbitals are situated in between the axis. But what about x square minus y square? For this should be 0. This should be 0 when s is equal to y or s is equal to minus y. That means along the axis there is probability of finding of electrons. So lobes are situated along the axis, and in between the axis there will be nodal surface. Okay, so in this way you can able to understand the size, shape and the orientation of different atomic orbitals. If you can understand the wave function, and if you can understand the radial part and the angular part. Thank you.